Chemical bonding, exceptions to the octet rule. In this tutorial, we will be talking about three main types of exceptions to the octet rule. The first being molecules in polyatomic ions that contain an odd number of electrons. The second being molecules in polyatomic ions in which an atom has fewer than an octet of valence electrons. And the third being molecules in polyatomic ions in which an atom has more than an octet of valence electrons, otherwise known as an expanded octet. Finally, I'll be showing you some worked examples. Type 1, odd number of electrons. In this type of situation, the number of valence electrons overall is odd. So complete pairing of electrons is impossible. Let's look at the example of nitrogen monoxide. So in this situation, we have nitrogen with 5 valence electrons for a total of 5 electrons to work with, oxygen, which has 6 valence electrons to give us 6 electrons to work with, for a total of 11 valence electrons, which results in 5 pairs of electrons and 1 electron left over. So when we work this out, we have nitrogen and we have oxygen, the 5 valence electrons of nitrogen, so 1, 2, 3, 4, and 5, and then the 6 valence electrons of oxygen, 1, 2, 3, 4, 5, 6. And if we move these valence electrons together to try to form as many shared pairs as possible, this is what happens. We move one electron, and then we move another, and then we have this 1 electron left over with nothing to really bond to. So the Lewis structure for this will look something like this, with this 1 electron being over the nitrogen and oxygen having its full octet, but nitrogen being electron deficient. Now you might be saying, well, Dr. English, we've just talked about resonance structures. Couldn't you have another situation where one of these valence electrons actually goes over to the nitrogen and the oxygen is electron deficient? And yeah, you can. It looks like this. So then you might be wondering, well, what is the better option out of the two? And of course, we come back to the idea of formal charges. So looking at this top Lewis structure, we have nitrogen, 5 valence electrons, 3 electrons total acting as non-bonding electrons, 2 bonds between the nitrogen and the oxygen, and if we add that all up, we get a formal charge of 0. Now looking at the oxygen has 6 valence electrons, 4 electrons involved in non-bonding electron pairs, 2 bonds, like we saw before, and its formal charge overall is also 0. So far, this is looking like the better option. We compare that to the other resonance structure of NO, which is nitrogen, 5 valence electrons, 4 electrons this time involved in non-bonding electron pairs, plus the 2 bonds between the nitrogen and the oxygen to give us an overall formal charge of -1. And then we have the oxygen, 6 valence electrons, 3 electrons involved in the non-bonding electron pairs, 2 bonds between the oxygen and the nitrogen for an overall formal charge of +1. So our original Lewis structure on top, with nitrogen being electron deficient, this is the better option between the two, which makes sense if you think about it, because really the oxygen should have that extra electron because it is more electronegative compared to the nitrogen. Let's do another example, looking at the molecule NO2. So in this situation, we have 1 nitrogen, 5 valence electrons for a total of 5 electrons to work with. Now we have oxygen, but we have 2 oxygens, 6 valence electrons apiece, total of 12 electrons to work with, for a total of 17 electrons, which is 8 electron pairs and 1 extra electron. So when we do this, we're going to put the nitrogen in the center as our central atom, and then an oxygen on each side, and then we're going to connect these oxygens to the nitrogens with a shared electron pair. So that is 2 shared pairs used out of a total of 8 electron pairs, which leaves us with 6 electron pairs left over. So let's start putting these 6 electron pairs around each oxygen. So 1, 2, 3, 4, 5, 6, and then we put the 1 extra electron on the nitrogen. Now this would be good, but you'll notice that the nitrogen is not just slightly deficient, it's severely deficient because it only has 5 electrons out of the 8 that are necessary. So that means we're going to take one of these shared pairs off of the oxygen and make it into a double bond between the oxygen and the nitrogen. So we'll remove it, we'll make it the double bond, and now we have our structure for nitrogen dioxide. And that's another example of a molecule with an odd number of electrons. Type 2, less than an octet of valence electrons, otherwise known as electron deficient species. In this scenario, we have fewer than 8 valence electrons around an atom in a molecule or polyatomic ion. These are most often encountered in compounds containing boron and beryllium. So the example that we're going to look at is boron trifluoride. So we're going to have 1 boron with 3 valence electrons for a total of 3 electrons to work with. Fluorine, we have 3 fluorines, 7 valence electrons apiece, for a total of 21 electrons to work with, for a total amount of electrons of 24, which is equal to 12 electron pairs. So we're going to put boron in the center, and then we are going to equally distribute the fluorines all the way around the boron. Then we're going to connect each fluorine to the boron with 3 shared pairs. So that's 3 shared pairs out of the 12 electron pairs that we have to work with, which means that we have 9 electron pairs left over. We're going to use those 9 electron pairs and distribute them around each of the fluorines. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So between the 9 non-bonding electron pairs, 10, 11, 12, we have all 12 electron pairs used. Now, boron is absolutely fine this way. The boron atom is said to be electron deficient. The boron atom can achieve an octet by forming bonds with compounds containing non-bonding electron pairs. So BF3 is very, very stable, but it can get the octet if it wants to, if it's coupled to the right compound, which I'm now going to show you. So the example here is NH3BF3. Boron trifluoride will react with a non-bonding electron pair on the central nitrogen atom of NH3 to form the compound NH3BF3. Boron will achieve a full octet of electrons through the formation of a specific type of covalent bond called a coordinate covalent bond, otherwise known as a dative bond. So we're going to set up the BF3 portion of this just like we saw on the previous slide. So a boron, 3 fluorines, single bonds between them, and then we're going to put the lone pairs all the way around the fluorines. Then, snuggling up right next to the boron, I'm going to put a nitrogen, and then I'm going to distribute 3 hydrogens, 1, 2, 3. I'm going to connect those hydrogens to the nitrogen through single bonds, 1, 2, 3. And then I know that nitrogen is going to have a lone pair off the side of it. So lone pair right there. So this lone pair right here is shared with the boron. So the boron will now have its full octet, 2, 4, 6, 8, because it's sharing this lone pair with the nitrogen, because now the nitrogen also has its full octet, 2, 4, 6, 8. So this sharing of these electrons from this non-bonding electron pair between the nitrogen and the boron is a very specific type of bond called a coordinate covalent bond. Type 3, more than an octet of valence electrons. And this is the most common type of exception to the octet rule that we see. This is known as expanded octets. Type 3 consists of molecules or polyatomic ions in which there are more than 8 electrons in the valence electron shell. This is also known as an expanded electron shell. Expanded electron shells only occur with elements located in period 3 and beyond in the periodic table. Elements in period 3 have electrons in the s, p, and d sublevels, which are available to form bonds. The empty d orbitals are available to accommodate additional electrons. The larger the central atom, the larger the number of atoms that can surround it. An expanded valence shell occurs most often when the central atom is bonded to smaller radius, more electronegative atoms such as fluorine, chlorine, and oxygen. So let's look at the example PCl5. So we have one phosphorus, 5 valence electrons, for a total of 5 electrons involved. Then we have chlorine, 5 of them with 7 valence electrons apiece for a total of 35 electrons. Add the two together and we get 40 electrons or 20 electron pairs. So we're going to start with the phosphorus in the center. And I'm going to distribute these chlorines in a very specific way that's going to lead into the next unit of molecular geometry. So I'm going to put a chlorine at the top, and then one off to the side, and then also to the side, one on the very bottom, and then one on the opposite side. Then, like we have done before, I'm going to connect the phosphorus to each one of the chlorines. 1, 2, 3, 4, 5. Now, I know you are noticing here that the chlorine on the top and the bottom are connected to the phosphorus with a black line. That's representing one plane. And then the chlorines attached to the phosphorus with the blue lines are representing another plane. And again, this is going to lead into molecular geometry. But for right now, what you need to know is that there's 1, 2, 3, 4, 5 shared pairs surrounding this phosphorus out of the 20 electron pairs that we have to work with. So 5 have used, 15 are available. So let's see if we have the 15 to use here or if we have to form a double bond or a triple bond. So here's our 5 shared pairs. Then we have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we had 20 electron pairs to use. We have used all of these electron pairs, and we have a neutral molecule of PCl5. So now if we were to look at this in terms of a 3-dimensional instead of a 2-dimensional view, it would look something like this. So these 3 chlorines here, here, and here are all in line with the page. This chlorine is going back into the page, and this chlorine is coming out of the page. So we can sort of visualize how these chlorines are arranging themselves in this expanded octet. And trust me, we will get into this more when we get to molecular geometry. Now let's look at an example of XeF2. Yes, we are working with a noble gas. Yes, some noble gases can bond with, well, really fluorine. So we have one Xe, 8 valence electrons, so a total of 8 to work with. 2 fluorines, 7 valence electrons apiece for a total of 14 electrons. Add them together, we get 22 electrons for a total of 11 electron pairs. So we're going to put Xe as our central atom, a fluorine to the left, a fluorine to the right. We're going to connect them together. So we have 11 electron pairs. We have used 2 of those electron pairs, and now we're going to complete the octets for each of the fluorine. So there's 2 shared pairs, and then 3, 4, 5, 6, 7, 8. So now we have 3 electron pairs left. Now remember, way back from the beginning of the chemical bonding unit, if you have extra electrons, you put them on the central atom. And in this case, we have 3 extra electron pairs. So you would arrange these like so. 1, 2, 3. Now you might be saying to yourself, but what the heck does that look like? And luckily for you, I have a little PhET animation to show you that will show you how these lone pairs are arranged around the XE. So you can see that the yellow spheres are representing the fluorine, and then each of the lone pairs coming out of the XE are coming out at these angles as far away from each other as possible. So it's pretty interesting to look at, and we'll talk more about what this arrangement is and what do we call this when we get to molecular geometry. But at this point, I just want you to know that it can exist. Yes, you can put 3 non-bonding electron pairs around XE. So what did you learn in this tutorial? We talked about 3 main type of exceptions to the octet rule. The first dealing with an odd number of electrons, the second dealing with fewer than an octet of valence electrons, and the third dealing with having more than an octet of valence electrons. And then we did worked examples at the end. Need more help? Feel free to contact me. Have a great day.